over and over again throughout the rest of your high school math careers. Okay? These two ideas, domain and range, are going to be something that you talk about all the time. Okay? So we need to make sure we understand it. The sooner we understand it, the easier it makes those other things that we talk about with domain and range. Okay? I saw in the last class, I think somebody told me 76 days we've been in school or something like that.
Wait, yeah?
Yeah, that's what they told me. A lot.
Hey, did you know Mr. Milton has mice in his house?
A lot of people have mice in their house.
He said I was quiet. We've been here for 1 and 2 months, and each month at least 30 days, so that's...
Right, but we don't come in on weekends.
Oh, you dummy. Shut up. That's how you teach yourself.
So listen. So, in my other algebra class, okay, which is essentially like algebra it's almost that. It's like algebra 2. It's basically the repeat of algebra 2. We've talked about domains and ranges probably 72 of those 76 days. Okay? So this stuff, as you guys go into algebra 2, this is going to be something that becomes very, very prevalent. Okay? Becomes very repetitive. Okay? So we need to make sure we understand this stuff. Okay? A relation. Okay? You guys know what relations are in everyday life, right? Okay? Somehow, let's say that I've got a link between me and a cousin. The relation that would be relation, right? We are related to one another. But how are we related would be the actual linkage. Does that make sense? Like how, are they my mom's brother's kids, or are they my mom's cousin's kids, or something like that? So are they first cousins, second cousins, that kind of thing, right? But we're related as cousins, and then there's a link that shows us how we're related. Does that make sense? Okay, mathematically, we do the same type of thing, but we do it with numbers. Okay? Well, this is important, so let's put aside all the goofiness and listen. A pairing of numbers in one set, D, with the numbers of another set, R. That's what we call a relation. Okay? It's just some type of way of showing how essentially input values or X values are related to output values or Y values. Okay? So, we had a problem the other day that we wrote a formula for, was that the waste in a landfill was equal to 50,000 plus 420 W. Or sorry, not W, months, M. Okay? And what we had then is, we created a chart where if months is 0, 1, 2, 3, so forth, then we should be able to find out the waste. So if it was 0, the waste was 50,000. If it was 1, it was 50,420. If it was 2, it's 50,840. Remember doing that question? Okay. So 0 is from this set D. Okay. So these numbers here are from a set D. Does that make sense? Okay. These numbers come from another set called R. Okay. They're related to one another through that rule right there. That's the link. Does that make sense? That would be kind of analogous to me having a first cousin or a second cousin or a third cousin. It tells me how they were related. Okay. A lot of times when they talk about relations, they're going to give you either the rule, like I've got in that box there, or they might just give you a list of ordered pairs. Okay. Or they might give you a graph, which is essentially still just a list of ordered pairs. Okay. But a relation is just linking things from one set of numbers to another set of numbers. Okay? A function is a special type of relation. Does that make sense? Okay? So I have cousins, but I have first cousins, second cousins, third cousins, and so forth, right? Okay? Which means I have special types of cousins. Okay? Which means the first cousin is a little bit different than the second cousin, a little bit different than the third cousin, right? So when we talk about a function, it's still a relation, but it's a special type of relation. It's like when we talk about triangles. If I have an isosceles triangle, is it just a special type of triangle? Is a right triangle still a triangle, but a special type of triangle? Does that make sense? So a function is a special one, okay, a special relationship. And it's one in which it says every x value, okay, every x value is paired with one and only one y value. So each x value is paired with one and only one y value. That is extremely important, okay? That's kind of what all of this set of notes is going to be about today and tomorrow, is when they give me some relation, maybe a set of ordered pairs. It might be something we call a mapping. It might be in a table. It might be in a graph. Okay. It might be the algebraic rule, the equation. And they ask me, is it a function? I have to see if what they're giving me matches that definition. If each x value gets matched with only one y value. Okay. And we'll come back and we'll, every time they ask that question, we're going to first say, okay, well, remind ourselves what function means, and then see if what they've given me matches that definition. Okay? Set D and set R that are described here in this relation. Okay? D stands for domain. Okay? So set D is domain. R stands in for range. Okay? Now, if you remember back into section 4.2, I gave you some notes that had this image on it right here. Remember seeing that vaguely? And I said these were synonyms, right? These were all equivalent words for the same thing. Okay? You see domain there? You see x values there? So domain and x values are, to us, the same thing right now. Okay? So, when we see the domain or ask about the domain, that's your independent variable, that's your x-axis, or your x values, and eventually we'll talk about them as input values. They're the numbers you substitute in. So over here, wasn't one an input value that I put in right there, that I substitute in right there? Was one then the next one that I substituted in right there? And then 2 and 3, right? Those were the ones that I put into the rule. So those are my inputs, so those are my domain values. Once I put those in, I had to do some algebra, and these were the results of that algebra, right? Those are the numbers that got spit back out to us. Those are our outputs. So those are our range values, or our dependent variable, or our y values. Okay? Let me say, one of the connections that we want to make is that ordered pairs, when you make an ordered pair, what is the coordinate that goes here? That's x, and then this one is y. Okay? Would you say that x and y are alphabetical? X comes before y, right? Look at domain and range. Which one of those comes first in the alphabet? D. Range comes second, right? Does that kind of graphic right there help you remember which one's x and which one's y? Okay, x and y are alphabetical. Domain and range are alphabetical, so match the ones that come up together first in the alphabet. So x and D. And then match the ones that come second, Y and R. Okay? I think that's the best, easiest way to remember these things. Because people get them mixed up all the time. They get them backwards. Okay? So make sure that you understand that, you know that, or develop some tool that you can remind yourself of in regards to those terms. Okay? So this is, I told you yesterday, this isn't going to be all that of a tedious task or a difficult concept. Basically what they're going to do is they're going to give you a relation. And like I said, the way they give you the relation, there's varying ways, varying techniques of doing it. And I'm going to try to show you as many as I can. Okay? But this is just one. They're going to give you just a list of ordered pairs. Okay? That's considered a relation. Okay? They might give you a list of ordered pairs. They might give you a graph of those ordered pairs. They might give you a table. They might give you a mapping. But they're going to somehow give you a series of ordered pairs. Okay? When they ask you then identify the domain, you're going to go through and you're going to pick off the x values from that list. Okay? So would you agree that 1, 3, 5, and 7 are my x values? So then I write my domain, I write it that way. 1, 3, 5, 7. Okay? That's all I've got to do. Is that pretty easy? So then if they want the range is just your y values, right? So 2, 4, 6, 8. And I write it that way. Now, if I zoom in on this, you see the curly braces, right? You have to use curly braces to tell people that you're writing a list. Okay? What we want to make sure is that we have no repeats. Okay? Another thing is order is unimportant. Okay? We cool with that? Okay? So if I write 1357, but you wrote 7531 or 5317 or 3571 or 3517, we're all the same, right? You have the same X values identified as I have. And that's what matters. Okay? We good with that? So on your homework, there's going to be times where you have to type in a list. There's no particular order. Okay? It's set up in the background that as long as it captures the correct values in any order, it will match your answer to what they've got. Okay? Okay. So let's do a couple examples of this. If I ask you, what is the domain of this list right here? Domain. We make our curly bracket.
3, 4, 8, 1, 2.
Okay, so you went through and you found the X values, right? 3, 4, 8, 1, 2. Good. So 3, 4, 8, 1, 2. And most time, guys, people aren't going to take the extra time to rewrite those in order because it doesn't matter. So they just write them as they see them, right? Okay. Now the range then. Yep. That 1, that 7, that 2, that 9, that 11. 1, 7, 2, 9, 11. Any repeats? Nope. So I don't have to worry about anything, right? Got my domain and my range. Is that cool? Okay. Here it says identify the domain and the range. So, domain. 4, 3, 1, -2, and -4, right? Any repeats? 4, 3, 1, -2, -4. Range. 1, 4, 2, 7, -2. Any repeats? Nope, we're good, right? So the idea is if you would have had like the 0.43 as well, where you had a 4 there, you have 4 there. We only want to show up one time in our list. Okay, is that doable? So make sure we don't put repeats. Now that's me showing you a domain in range or a relation in this case using just ordered pairs. But can I do the same thing this way? If I ask you to take this image here and tell me the domain and the range, okay, can we do that? The domain here is going to be all the X values that show up, right? So what's the X value at that point? -6. That's kind of hard to see. Let me labeling. My bad. Okay, so we got -6. What's the X value of that one? -4. -2. Oh. 2 from this one. 4 and 6. Is everybody okay with that? The range then? Range for A? 2. B? C? D? -2, right? Okay, now look at this one. What's the range value for E? 2. Did I already have that in my list though? So don't write it again. What about the range value for F? 4. Was that already in my list? So don't write it again. Okay? So you might have, 6 domain values, but only 4 range values. You might have 6 domain values and only 1 range value. Okay? You can have they don't have to be 1-to-1, meaning I don't have to have 6 of each or 7 of each or whatever. Okay? So that's one way, right? Can I do something like this? I don't know if this will change things to a table for me or not. I thought there was there we go. Relation. Alright, it doesn't put it in the table. But if I had, going back up to this one here, this is what we've been working on lately, right? And making these tables and turning those into ordered pairs. Well, when we make an ordered pair, this was 0, 50,000, 1, 50,420, 2, 50,840. Okay? And then you saw that was your independent, so that was your domain, and this was your dependent, so that was going to be your range. What? Alright, so the next statement here says construct a mapping diagram for the above ordered pairs. So I didn't give myself enough room here, so come to the side here. I'm going to make a mapping of this information. So what I'm about to write should go right there. Okay, so this is what we do. If we're going to make a mapping, you put a bubble. Okay? And that bubble is going to have your domain values in it. So you put D above it. Okay? And then you just put these numbers in there. So 4, 3, 1, -2, -4. Those are that list right there, correct? Okay. Then I'm going to put another bubble. And what do you think is going to go in that bubble? The range. Okay. So 1, 4, 2, 7, -2, right? Okay. The next thing that you do when you make a mapping is you show what 4 should be paired with. Okay. So if we go back to our list of ordered pairs, 4 was paired with 1, right? Does that make sense? 4 went with 1. So this is what we do. We just draw an arrow from 4 to 1. Okay? Now, it has to be an arrow. All right? And the arrowhead has to be pointing towards the object in R. Okay? Does that make sense? And then what does 3 go with? 4. What does 1 go with? 2. -2 went with 7. -4 went with -2, right? Okay. Now that's a pretty clean looking map. So I'm going to do this a little bit just to show you that this is okay. This happens because there's nothing that structures this and says you have to have. Maybe I go -4, -2, 1, 3, 4. Maybe I went in that order when I wrote those, so I just went from bottom up there. And let's say I kept the range as 1, 4, 2, 7, -2. If I go back to, I said 4 had to go with 1, right? So we go there, right? 3 had to go with 4, right? So we're there. See how those crossed? That's okay. 1 goes to 2. Those cross. -2 goes to 7. They cross. And -4 goes to -2. They cross. So it doesn't matter whether they cross or don't cross or all of them cross or just 2 of them cross, whatever. You should. The reason we do this graphically is so that you can put your hand on 4 and follow the arrow, and it takes you to the 1 that it should be with. Does that make sense? Okay. Now, when this happens, okay, we're going to ask ourselves, is this relation a function? And this is one of the reasons we draw this picture. Because it says, by definition, a function says every x value has 1 and only 1 y value. That's what it means to be a function. Does this x value have 1 and only 1 y value that it goes with? Yes, and that one y value would be 1, right? Now that needs to be true for every x value that you have in here. So does 3 have 1 and only 1 y value? Yes. Does 1 have 1 and only 1 y value? Yes. Does -2? Yes. Does -4? Yes. Okay. So because I'm able to say yes, each one of these x values has one and only one y value, this thing is a function, which remember is a special relation. Okay? When I look at this next one, okay, so if we look at one that is a function, we usually want to look at things that are not functions. So what is your domain for this relation here? 6 and 4. Okay? So your domain, remember we don't want repeats, right? So 6 shows up twice, I write it once. 4 shows up twice, I write it once. The range, 5, 3, 4, 8, right? And now the question is this a function or not? Well, if I look at this as a mapping, this is my domain bubble, which should have 6 and 4 in it. This is my range bubble. What should I put in that bubble? 5, 3, 4, and 8. Okay. Now, when I make the mapping, 6 from my order pairs, right here, 6 goes to what? Goes to 5, right? What does 4 go? 4 goes to 3. And then I get to this next one, 6 goes to 4. Okay, now here's the question, and then I can finish this off by making 4 go to 8 as well. Okay? But if I just look at this right here, when I highlight that right there, do we see that 6 as an x value has 2 different y values? Okay? Does that break the rule of a function? A function says that every x value has one and only one y value, right? This is saying the x value 6 has 2 y values. That's a contradiction of the definition. So this is not a function. Does that make sense? Not a function. Why do we want things to be functions? Or why do we want to be able to talk about things being functions? If I look at this, I say, everybody look at the x value that goes, or sorry, everybody look at the y value that goes with 6. What are some people going to be looking at? 5, right? What are some other people going to be looking at? 4, right? Okay. So there's ambiguity or vagueness there in which y value I wanted everybody to look at. Okay. Well, with a function, that ambiguity should be removed. If I look up at, let's say ambiguity, or maybe we even change the word to confusion. Okay. If I look at this and I tell you, everybody look at the y value that goes with 3, is everybody looking at the same number 4? Yes. Okay. Do you see how that's different in this situation than the one we just did? So a function means that no matter how many times you plug 6 into your equation or your rule, it's going to spit back the same number every single time. Okay? Did we talk about like a juicer or a food processor a couple of weeks ago? Like if I've got a food processor that like chops up fruit, right? If I put an apple in it, what am I going to get out? Applesauce. If I put another apple in, what am I going to get out? Applesauce, right? Put another apple in, what am I going to get out? Applesauce. If I put an apple in every single time, what am I getting out? Applesauce. So algebraically, that food processor is a function. For the same input, I always get the same output, right? That's what we should expect. Like all our kitchen appliances are essentially functions. Okay? Does that make sense? Okay? Put bread in a toaster, what do I get out? Toast. Every single time, right? I'll never put bread in a toaster and get out milk, right? Okay? So the idea is the same mathematically. We should be able to plug in a number and always get back out the same number. So for instance, let's just kind of see where this is going to go. If I have the equation y equals like 2x, just something really easy, okay? If I plug x in to be 3, what is y going to give you? If I plug x in to be 3, y is going to be 6, right? Do it again. Put 3 in. What's y going to be? 6. Do it again. X is 3. What's y going to be? 6. No matter how many times you put 3 in, you're getting 6 back every single time, right? Now, there are some things that are a little bit different. If I do this, I have something like this, an equation like this, okay? Or let's actually, this is fine. Okay? If I plug x in as 4, okay, I get y squared equals 4, right? You guys ever dealt with square roots before? Yeah. Square root is a number that I multiply by itself 2 times to get something, right? Okay? So if I take the square root of 4, okay, the argument is that I get 2. But 2 times 2 is 4, right? But isn't negative 2 times negative 2 also 4? So when we take square roots, we actually get 2 answers. Okay? So the argument here is, when I plug x in, I could get 2 back. Or if I plug x to be 4 in, I could get negative 2 back. Does that make sense? Is that a problem? That's not a function, right? Okay? So some rules, I can plug a number in and always get the same number back. So some rules, I plug a number in and I might get 2 results back that are different. Or I might get 3 or 4 results back that are different. Okay? So we need, that's kind of what this is trying to get us to recognize and understand as we work through the rest of this course and in the other algebra courses. The idea of putting something into a function and knowing that you're getting one and only one thing back. Okay? What if I had something like this? What if I had a list? I'll do another mapping here. What if I had the ordered pairs 2, 3, 3, 3, 4, 3, and 5, 3. What's my domain? Okay. What's my range? Right, so I'm seeing all these 3s, right? So remember, we don't want redundancy, so we're just going to put 3. That's my range, right? Okay. Now the question is this a function? Well, let's draw a map. If I go 2, 3, 4, and 5, that's my domain, right? My range is 3. What did 2 pair with? 3. What did 3 pair with? So these all paired with 3, right? Okay. Is that a mapping? It is a mapping. Is that a function? No. Why not? Okay. Does that violate the rule that says for every x value, there is one and only one y value? Yeah. There's one and only one. So you're telling me that when I say at x value, so I tell you a specific x value like 2, Lindsay. Wait, come on. Do you know the one and only one y value that goes with it? What's that one and only one y value? 3. Okay. So then I tell you another x value 3. Do you know the one and only one y value that goes with that? Yeah. What is that y value? 4. 3. Okay. If I say x value of 4, what's the one and only one y value that goes with it? 3. If I tell you an x value of 5, what's the one and only one y value that goes with it? 3. So did every one of those d values, every one of those domain values I gave you, have one and only one y value that you're able to spit back? Yeah. Okay. It doesn't say anywhere in our definition that one and only one y value can actually be the same number for multiple x's. Does it make sense? The issue is when you have, if you compare this to the other graph that we drew that was not a function, the issue is that when it's not a function, there are 2 arrows or 3 arrows or 4, it doesn't matter how many, more than one, coming out of a domain value and going to separate y values. Does it make sense? But you can have a bunch of arrows going to the same y value. Okay? I personally believe, and this is just because of my experience, and remembering back when I was in 8th and 9th grade and doing this stuff, I struggled with that picture and determined whether something was a function or not. Okay? But I understood that these mappings, listing of ordered pairs, graphs, tables, they are all different visual representations of the exact same thing, right? Do we understand that? Like that picture right there is a visual representation of the ordered pairs 2, 3, 3, 3, 4, 3, and 5, 3, right? Do we also agree then that graphs are visual representations of relations? If I look at this relation right there, and actually let's wipe this first one out right away. Eliminate that first one. Okay? And I always want to graph those 4 points. If I graph those 4 points, it's negative 3, 1, 0, negative 2, negative 4, negative 1, and 1, 2. Okay? If I graph those 4 points, okay, so that's a relation shown as a list of ordered pairs, and then I have the relation shown as a graphical picture, right? Does that make sense? So those two things say the same thing. This list and that show the same thing. If I were to make the mapping, the domain and the range, negative 3, 0, negative 4, 1, 1, negative 2, negative 1, 2, and I show the mapping, that should say the same thing that says, same thing as that says. Does that make sense, everybody? So 3 different ways of representing the same information. But if I'm trying to determine whether something's a function or not, the easiest thing I think, and I would argue that probably 99.9% mathematicians are going to say the same thing, is to view your data points in a graph and make the argument whether they're a function that way. So this is what we do. If you read this up here, it says we're going to apply what we call the vertical line test. The vertical line test says you're going to take a line that is vertical. So I'm just going to make that blue line right there. And what we're going to do is we're going to make that blue line mobile. We're going to move it left and right. Okay? And if it ever crosses your graph 2 times, you fail the vertical line test, which means then you fail the function test. So it won't be a function. Okay? And we'll talk about why that happens. Okay? If I look at taking this vertical line and moving it through here, okay, now I'm only interested in where that vertical line intersects my graph. So would you agree right there, intersects my graph? So I'm going to check. When I let that vertical line stay right there, does it only intersect my graph or my data, my point, 1 time there?
Well, you're missing a point, so that doesn't help.
Well, I told you at the beginning I wanted to delete that point out. Okay? If I look at taking that blue line then and moving it there, does it only pass right there 1 time? Okay? So far I've passed the vertical line test in each situation. I have to make sure it does that all the time. So does it pass right there? Yes. Does it pass right there? Yes. So it passed everywhere. So that means this thing passes the vertical line test. If you pass the vertical line test, that's a way to say, yes, it's a function. Okay? Now, you're right. I did leave a point out. That point, negative 4, 2, right? So let's put negative 4, 2 in. Right there. And now when I move that line back, do I still pass there at negative 3? Do I pass there? Do I pass there? Do I pass right here? No. Okay? And what that means then, think about this. So that means I failed the vertical line test, and that means this is not a function. But why does the vertical line test work? Why does this connection make sense? Think about this. What would be the x value that goes with that point right there? Negative 4. What's the x value that goes with that point right there? Negative 4. And I tell everybody look at negative 4 and tell me what is the y value that goes with negative 4. Are some people going to tell me 2? Are some people going to tell me negative 1? Okay, so that's the idea that x value does not have 1 and only 1 y value, right? In this case, it's got 2 y values. Okay? So when you fail the vertical line test, it's not a function. If you pass the vertical line test, it is a function. Okay? So that's the easy. I think that's the easiest. So I'm going to give you lists, of ordered pairs. I'm going to give you mappings like this picture here on the bottom right. And if I ask you, is it a function or not, and you question whether you can read this and determine, because there's a way to read this and determine if it's a function. Basically, I'm just going to see if there are any x's that repeat. Are there x's that repeat? There are. So then I have to make sure if those y's are different for those x's that repeat, then it's not a function. Okay? Here, the thing was if there are two arrows kind of emanating from the same x, then it's not a function. Okay? But if I struggle remembering those or using those two tools, this is my go-to. I'm going to graph the ordered pairs. And I'll make that vertical line pass through there and see if it passes. Okay? Now, here's the thing. You can pass your vertical line test an infinite number of times. Okay? An infinite number of times. So let me show you a picture here. All right, so would you guys agree that a graph like this is a series of ordered pairs? It's just an infinite number of them, right? And they're so packed together, so close that it creates this smooth curve, right? Would you agree that if I put a vertical line in here, let's say, if I put that vertical line in there, do I pass the vertical line test over here? Okay. Only intersecting one time, right? So I intersect an infinite number of times here one time. So I'm passing it an infinite number of times. But do I fail it right there? Do I fail it there? Do I fail it there? Okay. So even though I pass it a lot more than failing it, I'm still failing. Does that make sense? It's the I told the last class. I could be a perfect human citizen and never be convicted of a crime or anything like that for 35 years. Okay? Perfect citizen. But if I go and rob a bank tonight, what am I known for my entire life? A criminal, right? A robber, a felon, whatever, right? But I was good for 35 years, crime today, good for the next 35 years, because I'm going to go to jail. Okay? And I can't be bad there, right? So 70 years of my life, I am a good person, good citizen, contribute. Okay? But I made one decision that made me a felon and identified as a felon forever. Does that make sense? So one bad egg makes them all bad. Does it make sense? So you fail one time, you fail all the time. Okay? And that's something to think about when we want to identify what a function is using the vertical line test. I just need one place of failure. Okay? We'll finish this off tomorrow. There's some other different techniques that we can use to identify functions. And then there's a special type of notation that we use so that we automatically know when that notation is presented to us that the thing that they're giving us is already known to be a function, which is nice for us. Okay? So we'll talk about that tomorrow. I've assigned a math Excel assignment. It's not going to be due tomorrow.